Great, so today we'll look at section 4.2. We're going to do the first half today, we'll do the second half tomorrow. And we're going to kind of look at graphing, but we're going to break it into cases. So sometimes when you graph a rational function, just to show you an example, the exponent in the top is smaller. Sometimes when you graph it, the exponent in the top is bigger, or sometimes they're the same. So we'll look at all those different cases over the next couple of days. Okay, so one thing to keep in mind is when you have an asymptote and when you can have what we call a hole. A hole is also called a removable discontinuity. Okay, we consider it removable because it's such a small discontinuity, you almost can't even see it. Okay, that's what it means if it's removable. An asymptote would not be considered a removable discontinuity. Okay, asymptotes are very obvious because the graph usually does something like this. It spikes up, very high on one side, and sometimes it goes down on the other side. But removable would look something more like this. A small hole in the graph, right there. Okay, so removable just means it's a very, very small discontinuity. And usually, when you have that kind of discontinuity, you can't see it on the calculator. Okay, no matter how much you keep zooming in, you'll never see a hole in the graph because the hole is infinitely small. Right? If you had a removable discontinuity at 2, you're going to be fine at 1.999999999. You're going to be fine at 2.000000001. Okay, so it's an extremely small spot, just exactly the number 2, that it doesn't work. And that always happens when you have a common factor in the numerator and the denominator. All right, so let's graph that. And what value is not in the domain in this one? Sam?
1.
1. Now, would you expect to see a vertical asymptote at 1? Or would you expect a hole at 1? What do you think is going to happen with this one? Yeah?
A hole.
Yeah, how come?
Because it's the same in both the numerator and the denominator.
Yeah, you have a common factor in the top and in the bottom. So basically what this is going to look like is the line y equals 1. Because you're dividing two things that are the same. And if you hit graph, do zoom 6, that's pretty much what it looks like. But we know from looking at the problem that if you try to trace to the number 1, you don't get a value. Okay? Because it's a removable discontinuity. If you trace to point 99999, that's fine. If you trace to 1.00001, that's fine. You just can't type in 1. Okay, so that's what that one looks like. This one. What value are you not allowed to use in the domain for g of x? What, Trip? 1. Yeah, it's 1 again. Would you expect there to be a hole at 1 or an asymptote at 1? Hole. Yeah, it's going to be a hole because you have a common factor. This time, the numerator is a degree higher. So what's going to happen here is if you think of this 1, you have two things with the same base. If you subtract the exponents, this is basically going to look like x minus 1 to the first. This is going to look like a line with a slope of 1 and a y-intercept at -1. From the graph, you would never know there's a hole. That's the point. Okay. So any questions on when a hole occurs in your graph? Can anybody tell me one thing I could change there to make it so there's an asymptote at 1 instead of a hole? Yeah?
Change the top to like x minus 2 or something?
Yep. If you change that to x minus 2, Now you're still not going to be able to plug in 1, but it's going to be more of an asymptote instead of a hole. That's it. There's actually 2 kinds of asymptotes here. Remember I told you there's a slant asymptote or diagonal? That's what's happening here. There's a diagonal and there's a vertical. There's no horizontal. If you have an asymptote that's on a slant, you don't have a horizontal usually. Actually, I'll have to double check that, but there's definitely a vertical and a diagonal asymptote here, but no horizontal. Okay, so in the 2 examples we just did before I had Sam modify them, we had what's called a removable discontinuity. Okay, so all you would have to do to remove it would be something like this. Let's take the second one. And we write it as a piecewise function. So I'll make a new one. We'll call it h of x. And I'm going to say, use this formula for all x's not equal to 1. So anytime you give me an x value that's not equal to 1, I'm going to plug it into that formula to get my y value. If you give me a value that is 1, what I'm going to do to get the y value? Let's see. So for this one, we would want to define it so that it makes it look continuous. So let me change this back. So for every point that's not 1, you're going to use that formula. If it is 1, I would want the y value to be 0. Because if you made at 1, even though this formula doesn't have a y value when x is 1, but if I made the y value 0, then it would make my line continuous. So what I just did is I redefined the function at the 1 value that was a problem. And by doing that, I basically did this. That's the top graph, okay? Using it when x is not equal to 1. The bottom graph basically fills in the hole. So now you just created a continuous function. So any question on what I mean by redefining it at one particular point in order to make your function continuous? You basically redefine it so you fill in the hole, okay? And then that makes it continuous. Okay, you can't do that with a vertical asymptote, because with a vertical asymptote it's a little more complicated than a hole. The whole graph is messed up. Okay, it's not just a small section that's not connected. It's a huge section that's not connected. Okay, so we can't really fix that. All right, so suppose that we have 2 polynomials. Okay, what I'm writing here for f of x could represent something just like this. Okay, polynomial on the top, polynomial on the bottom. Usually it's in descending order. So highest exponent down to the constant. Okay, so we talked about the end behavior model. Okay, the thing that basically predicts what this is going to look like. So for the top, that's the end behavior model. It has the highest exponent, so ultimately it's going to control what the top looks like. What do you think the end behavior model for the denominator would be? Jane?
Would it be its first term too?
Yeah, it's the highest exponent term. So it would be b sub m x to the m. That's the end behavior model for the bottom. Now, we have a term that's going to predict what happens in the top. We have a term that's going to predict what happens in the bottom. What do you think you would do with the 2 of them to predict what's going to be happening in this whole fraction? about Leo?
Wait, what?
Any guess? What do you think you would do to predict what's going to be happening with this whole fraction? So we know what's happening in the top with the end behavior model. We know what's happening in the bottom. But now we want to know what's going to happen with the whole fraction. So what do you think we would do with the two end behavior models?
Combine.
And how would you combine them? What operation? Division. Yeah, we would divide them. So take the end behavior model for the numerator, take the end behavior model for the denominator, and divide them. Okay, so basically, as your x value starts to get bigger and bigger, this approximates what your function is going to look like. Okay. All the other stuff that has smaller exponents, in the big picture, it doesn't make a difference. Right, so I'll come right back to it, just to go back to the example I keep looking at, this one. That's going to control what happens in the top. That's going to control what happens in the bottom. So if you say to me x is 1,000,000, whether I take 1,000,000 and square it, double it, and then subtract 1, or just take 1,000,000, square it, and double it, I'm basically going to get the same thing. Okay, subtracting 1 when you're dealing with 1,000,000 squared times 2, it's not that big of a difference. Same thing here. If you take 1,000,000, cube it, and then multiply it by 3, it doesn't even really matter if you add the rest. That's going to be so small compared to what you did before it. Right? So that's why the other stuff doesn't really matter in the big picture. Okay? Certainly if you take a small value for x, like 5 or 6, you're going to get very different results. But as x gets really, really big, that's basically what your function would look like. Now, since we have division and we have the same base and we're dividing, what do you do with your exponents when you have the same base? Remember what you do? Like if you had like 2 to the 5th divided by 2 to the 3rd, what would you do with the two exponents?
Subtract them.
Subtract them. Okay, so what really ends up happening is you divide the leading coefficients for the end behavior models, and then you subtract your exponents. And that is the end behavior model for the rational function. And so it just involves finding both end behavior models for the numerator and denominator and dividing them. And now the next page, I already kind of circled and started the problem, but we'll look at that now. All right, so this one says find the end behavior model. We'll worry about horizontal asymptotes after. So I already circled it. 2x squared is the end behavior model at the top. 3x cubed is the end behavior model at the bottom. And then we'll simplify it. When I divide 2x squared by 3x cubed, what do I get? And if you have negative exponents, we just leave them in the bottom. Don't write your answer with negative exponents. Well, Rebecca, did you get that?
2 over 3x.
Perfect. 2 over 3x. That's the end behavior model. Any question on that? So that predicts if you were to graph f of x and graph the end behavior model and zoom way out, zoom your x-axis out to like 10,000, negative 10,000 and 10,000. These two graphs would pretty much look the same. Right? We won't look at all of them. We could look at this one quick. Right, so we get 2x squared minus 1 divided by 3x cubed plus 2x plus 1. Okay, so that's the original. I shouldn't need parentheses for 2 divided by 3x because there's no addition or subtraction, so the order of operation should be fine. And let's look at the standard window first. Notice it does take the calculator a while to draw these functions. And I lied, I do need parentheses. Let's look at it again. So it kind of looked like a diagonal line before. That's because my order of operations wasn't good. And actually that one, even zoomed in, looks, you can see on this section here that it's pretty much tracing the same thing. So now if you zoom out, let's just do like negative 500 and 500. You're not even going to be able to see the difference between them tracing along the x-axis. They're going to look pretty much exactly the same. That's what we're focusing on, the x-axis, as we head farther and farther away. Don't focus on what happens near the origin. End behavior means the ends, okay, towards infinity. And they pretty much look identical. Great. Any questions on that? Now, if this predicts what's going to happen as x gets bigger and bigger, you can use this to find your horizontal asymptote. Okay. Remember yesterday, we said horizontal asymptote is what happens to y as x gets bigger and bigger and bigger. So, to find horizontal asymptote, find horizontal asymptote, take your end behavior model and let x approach positive or negative infinity. Okay, so take your end behavior model, which is what we have the box around, and let x get really, really big and tell me what's happening to the EBM. Great. So first of all, Shauna, horizontal asymptote starts out with what letter?
Y.
Yep, starts out with y. Equals. And now, can someone else tell me what's going to happen to the end behavior model as x gets really, really big? What is the end behavior model going to approach? Sam?
0.
Yeah, it's going to approach 0. We can kind of see it in the picture. It's getting very, very close to 0. You could trace. If you trace, there we go. Yeah, so if you trace along it, look at the y value. It's getting smaller and smaller and smaller. 0.003, 002, as I keep tracing to the right. Okay, so algebraically, that's how you find the horizontal asymptote. Find the end behavior model, and then let x get really, really big. Any question on that? Yep.
Just with the exponents, when you're finding the end behavior model, why do you get rid of it? Like you're dividing the x squared by x cubed.
Yep.
You just end up with x in the bottom.
Yes, you end up with x in the bottom. Is that your question? Why?
Yeah.
So if you had 2x squared, think of it this way. Divided by 3x cubed. So everywhere you have the same thing in the top and bottom, you can cancel it. So we have an x in the top and the bottom, another x in the top and the bottom. So you're left with a 2 in the top and a 3x in the bottom. So your variable always ends up where the higher exponent was, okay? Because if you have more x's in the top, it ends up in the top. More in the bottom, it'll end up in the bottom. Unless the exponents are the same, then we'll see what happens there. Okay, how about Juliette? What's my end behavior model in the top here?
Should be 2x to the 4.
And in the bottom?
3x to the 4.
3x to the 4th. Okay. So what is my end behavior model going to be there? Yeah?
Would it be 2 over 3?
Yeah, it's going to be 2 over 3. So my end behavior model is just 2/3. All right. Now, I think they also want the horizontal asymptote. Okay, let's find that. So now, look at your end behavior model. Let x get really big in that end behavior model. What is the end behavior model going to approach as x gets really big? Leo?
2/3.
It's going to approach 2/3. There is no x. So what we're getting in this problem is a horizontal asymptote, but it's not at 0. Okay? So a lot of times when your exponent in the bottom is bigger, you always get a horizontal asymptote at 0. When the exponent in the top is the same as the exponent in the bottom, then all the x's cancel out, and then what you're left with is a constant for your end behavior model. That constant is your horizontal asymptote. Okay, so when exponents are equal, you get a horizontal asymptote not at 0. We didn't do one where the exponent in the top was bigger, and we won't look at that today, I don't think. At least in detail. We'll look at that more tomorrow. Okay. Any question on the end behavior model or horizontal asymptote here? All right. So, we're going to focus on the case where the degree of the numerator is less than or equal to the degree of the denominator. That's the two problems I just gave you. Degree of the numerator is less than, degree of the numerator is equal to the denominator. Okay. These are general suggestions. You don't have to do every step here every time because some graphs it might not apply to. Okay. What I like to do is if there's intercepts, those are always a good thing to find. Okay. If you can find where your graph is going to cross the x or the y-axis, do it. But keep in mind, not every graph crosses the axis. Okay. Here's a rational function, or part of one, that never crosses any axis. It's going to get closer and closer to the x-axis. It's going to get closer and closer to the y-axis, but you're never going to be able to find the intercepts because they don't exist. Okay. But if they do exist, we'll try and find them. Another thing that's helpful is the vertical asymptotes. To find your vertical asymptotes, find the zeros of the denominator. What's the only time that a 0 of the denominator is not a vertical asymptote? Yep.
It's diagonal.
I'm thinking more about the equation. So when do you get a whole?
Oh, nice.
When you have common factors. Okay. So your vertical asymptotes are your zeros of the denominator as long as you don't have any common factors. Okay. Next, we want to find the horizontal asymptote, if there is one. For the kind of problems I'm giving you today where the numerator, the degree is less than or equal to the denominator, I'm pretty sure every problem will have a horizontal asymptote. They should. And then after you find your vertical asymptote, what you want to do is check the behavior on each side of it. Usually what happens is, let's say you had a vertical asymptote at 2. Go to your table and plug in 1.99 in the calculator. You're either going to be up very high or it's going to be down very low. That's what happens near a vertical asymptote. It's either approaching infinity or negative infinity. And then you can always confirm what you think is going on with your graphing calculator. Okay. As I sketch these, I am going to use a graphing calculator through the whole process, but I'm not using it to sketch. The only thing I'm using it for is the table because it can plug in values very fast, much faster than I could do by by hand with a regular calculator. Okay, so we've got 3 graphs. We'll probably do 2 together, and then I'll leave the last one for you to see if you can sketch on your own. You'll start to see a pattern. A lot of these kind of graphs look the same every time. Maybe just shift it a little bit, something like that. Okay, so let's sketch a picture of that. The 5 steps that I just gave you up above, you can do them in any order. I generally like to find the asymptotes first. It's just the way I do it. So let's start with our vertical asymptotes, the zeros of the denominator. Okay, so let's set the denominator equal to 0, see if we can solve it. Okay, it's really nice if it factors because then we don't have to get involved with quadratic formula. Does anybody see how x squared minus x minus 6 would factor? Thinking of 2 numbers that multiply to give you 3 and subtract to give you 1. 2 numbers that multiply to give you 6 and subtract to give you 1. And I gave you one of the answers. Yep.
2 and 3.
Yep, so we're going to use 2 and 3. And what about my signs?
The negative would be on 3.
All right, so
Minus 3 plus 2.
Minus 3 plus 2, let's check. X squared plus 2x minus 3x, negative 3 times 2, perfect. So, I'm going to get 2 vertical asymptotes at 3 and negative 2. Okay, so let's, I like to we'll sketch those first. So I'm going to put an asymptote at 3. And I'll put another one at negative 2. All right, so there's 3 and negative 2. All right, so I've got the asymptotes that are vertical. Let's do the horizontal. All right, so we're going to find the end behavior model, and that'll lead us to the horizontals. What's the highest degree term in the top here, Trevor? What's the highest degree term in the top? 1. So that's a degree 0. I think I see a term in the top that has a higher degree than that. There's a linear term in the top. Or a degree 1 term.
Not sure.
What's the only other thing in the top? Besides the first thing we said.
Negative 1.
I think you said the first thing.
Oh,
Yeah, x. So x is the highest degree term in the top. What's the highest degree term in the bottom? Yep, Neil.
X squared.
X squared. So let's divide them out. What's my end behavior model here? Yep. Careful, you have more x's in the bottom. So your final answer is going to be x's in the bottom of a fraction. 1 over x. So that's your end behavior model, which now allows us to find the horizontal asymptote. What happens to that fraction is x gets really, really big. Well, what will that fraction approach? Sam?
Negative 1.
So like let's plug in like 1,000 for x. What's 1 divided by 1,000? Really, really small. Is it getting close to
0?
Getting close to 0? Yes. So your horizontal asymptote here is y equals 0. Any question on that? All right. So now let me put that in. And we've kind of broken it up into 6 sections, and I showed you something kind of like this earlier. What else can we find? We're definitely going to do number 4, but let's see if we can find the x-intercepts and the y-intercepts. Okay, so the y-intercept is when you let x equal 0. Well, if you let x equal 0, you get -1 in the top. Over, what's 0 squared?
0.
Minus 0?
0.
Minus 6. Minus 6. So, the y-intercept is 1/6. That's where it'll cross the y-axis. All right, so basically, just a little above the origin. It's going to go through that point. Let's find the x-intercept. So the x-intercept is when y equals 0. So basically, for that intercept, I'm asking, when is this fraction equal to 0? What value would make that fraction equal to 0? Yep.
1.
1. The only thing we have to check is the value that he just said. We have to make sure that it doesn't cause me to divide by 0. What value did you say again?
1.
1. Is 1 one of the numbers that would cause me to divide by 0? No. So then it will go through that point. So your x-intercept is at 1. Not sure those 2 points really helped me a lot. What is going to help me now is checking the behavior near the asymptotes. So I'm going to check a value just to the left, just to the right of each asymptote. To do that, I need to type it in because it's a lot faster to use the table than it is for me to try to do this by hand. All right, so we've got x minus 1 divided by x squared minus x minus 6. Okay, so my first asymptote is -2. Can somebody give me a number that is just to the left of -2, but extremely close to it? Yeah.
-2.0001.
Sure, -2.001. Or even that's okay. I'm down at -60. So just to the left of -2, I am way, way down on my graph. Let's make it a little longer. It's way, way down here, getting closer and closer to the asymptote. Okay, let's check a value just to the right of -2. Can someone else give me a value that's to the right of -2? About yeah.
-3.
What's that?
-3.
That would be to the left. And I want it to be extremely close, say within like 100th.
1.99.
-1.99. Bless you. So if we go just to the right of -2, now all of a sudden my graph is up. Very, very high. Now let's do the same thing with the other asymptote. Let's check the behavior at just before 3. So like 2.99.
How do you type in the table?
If you can't type in your table, you need to go to Table Setup, second window, and put the independent on Ask. And then it'll let you type in your table. So 2.99, the graph is down very, very low. And then what would be a value that's just past 3? About negative? What would be a value just after 3?
3.01.
Alright, so 3.001. And we're way, way up. Okay, positive 400. Alright, so now we need to connect these dots and see what's going on. With these kind of graphs, you never cross an asymptote. So if I'm in this section, which puts me somewhere in here, I have to stay in that section, but I have to get closer and closer to each asymptote. So what's going to happen is this part is going to come up. It's going to curve. It has to keep getting closer and closer, but it has to stay in that section. Same thing is going to happen in the upper right section. Okay, I've got a point right here, and I'm trapped in that area right there. But as x gets bigger and bigger, we already know in behavior model, it's approaching 0. So it's got to come down like that. Again, just getting closer and closer. And now in the middle section, it's going to stay trapped between those vertical asymptotes, and it has to go through all 4 points in the middle. So it's going to have to look something like that. Okay, let's hit graph and see how we did. That looks like their graph is a little flatter in the middle than mine is, but that's fine. So that's pretty much the same graph. Okay, so any questions on that? That's pretty much how you graph any rational function. Yep.
So that spot where it crosses the asymptote, would that be the hole? Would that be a hole in the graph? Or?
There's no holes in this one because we had vertical asymptotes. So holes would be in place of vertical asymptotes. The only numbers you're not allowed to plug in here are 3, which I can see as an asymptote, and -2. And that's it. So there's no holes in this graph. So it's okay to cross an asymptote near the origin. Okay? It's just as you get further and further out with these kind of functions, you do not cross the asymptote again. Other questions on that? All right, so we'll try. Let's try one more of those. What's different about this one compared to the last one? Something a little different here. Yep.
The highest exponent are the same.
Yeah, the degree in the top and the degree in the bottom are the same, which means you're going to get a horizontal asymptote, but it is not going to be at 0. Okay? So let's go through, and I've already kind of labeled the stuff we want to find. Let's start with vertical asymptote. Gracie, how do I find the vertical asymptotes?
You have to do set it equal to 0.
Yep, and what do you set equal to 0? The top or the bottom?
The bottom.
Perfect. So we're going to take the bottom. Let me make this page bigger. Set it equal to 0. Now this one, the factoring is a little more straightforward. Just factor out an x. And you're left with 2x minus 5. And now we can write down our 2 vertical asymptotes. The first one is at x equals 0. And where would my second asymptote be? Yeah, 5/2, or you could write 2.5. Now, some people like to do all the work first and then all the graphing second. I kind of like once I get something to then sketch it. So I'm going to put the asymptotes in. At 0 and 2.5. So there's 0 and 2.5. Let's do horizontal asymptotes. So horizontal asymptotes, you're going to find your end behavior model. Okay. Before you reduce it, can anybody tell me what the end behavior model would be? Yeah.
3x squared divided by 2x squared.
Perfect. And now 3x squared divided by 2x squared turns into 3 over 2. Now, take your end behavior model and let x get really, really big. What happens to this fraction as x gets really, really big? Yeah?
It approaches 3 over 2.
Yeah, it's going to approach 3 over 2. There's no variable. This is a constant. So nothing's going to happen to it. So let's put in a horizontal asymptote, which I should write down. Some people find the decimal easier when they're graphing, just because they know where it is. So you can change it if you want. 1.5. All right, so there's your horizontal. X and y-intercept. Okay, let's start with our x-intercept. So x-intercept is when the y value is 0. So in other words, when is this 0? The only way for that to be 0 is if the top is 0. So let's see what value would make the top 0. So 0 equals 3x squared plus x minus 4. Let's see if we can factor. We'd have to try 3x and x. Thinking that because 3 times 1 is 3, 1 times 4 is 4, and 3 and 4, if I subtract them, I get a 1. My signs would have to be one of each. And I think I would want minus, plus. Let's check. Minus 3x plus 4x is plus 1. Yep, perfect. Okay, so my x-intercepts are going to be at negative 4/3 and 1. So this one crosses the x-axis twice. Negative 1.3 and 1. So negative 1.3 is about there. So that makes sense because I'm thinking in this section it's going to look something kind of like that. We'll check that out. And then it's going to cross again at 1. Which is fine because that's in 2 separate sections. So that's good. Y-intercept. Let's plug 0 for x. Well, look carefully at that problem. Just look at the bottom first. What do you get in the bottom if you plug in 0 for x? You get 0. So what does that mean about my y-intercept? It doesn't exist. Okay, you cannot plug in 0 for x because if you did, you'd be dividing by 0 because that's where we have an asymptote. So this graph doesn't cross the y-axis. Okay. So the last thing to do is check the behavior near the asymptotes. Okay, we use our calculator for that. So 3x squared plus x minus 4, and it's a good idea to put that in parentheses. Divided by 2x squared minus 5x. Okay, let's start with our vertical asymptote at 0. Can somebody give me a number just a little smaller than 0? Bob, Leo?
Negative 0.01.
Negative 0.01. Okay, we're way, way down. And while we're here, let's do a number just a little bigger than 0. Tessa, what would be a number a little bigger than 0? Sure, 0.001. Maybe 0.01, that's fine. And then we're up very high. So just to the left of 0, we're way down. Just to the right, way up. So just to the left, way down. To the right, way up. Now that other one was, what was that? 2.5. Abby, what's a number just a little smaller than 2.5?
2.49.
All right, so 2.49. We're way, way down. Just after it, we're going to be way up. Okay, so to the left of it, you're down. To the right, up. So down, up. And now I think we've got enough information to make our sketch. Okay, so stay very close to that asymptote. Slowly getting away from it. Curving towards that asymptote. In the middle, think it's going to do... This is kind of a tough one to draw. It's almost vertical, but it's going to be a little bit of a curve to it. That's about the best I can do. Okay, so something like that. And then in this section, we've got that point there. It's going to come down and curve. If you want to find out exactly like how sharp of a curve that could be, you could always plot another point. You could do like 1, 2, 3, 4. You could let x equal 4 and let x equal 5. And that would give you a good idea of what your y value is. So I should go through the point 4, 4. 1, 2, 3, 4. 1, 2, 3, 4. So I should be right there. I'm a little bit off. That's okay. Okay. Let's look at the sketch and see how we did. Yeah, even the calculator had trouble with the middle section because it's so steep that it just stopped drawing it. Okay, but it should continue like we have. Okay, any questions on that? Okay. Same thing here. This line should continue down in that section too. Right, so those are basically the two types that you'll have. Okay, horizontal asymptote at 0, not at 0. So this one, just tell me where would the horizontal asymptote be?
At 0.
Yep, it would be at 0. How do you know that?
Because x over x2 is 1 over x.
Yep. Exactly. It's 1 over x, and then if you let x get really big, the horizontal asymptote would be at 0. How do you find the vertical asymptotes? Jay?
You set the bottom equal to 0, it's the roots.
Perfect. It's at the bottom equal to 0. Find the roots. How would you find the y-intercept? What do you do to find the y-intercept? Yep.
You set x equal to 0.
Yep. Plug in 0 for x. To find the x-intercept, plug in 0 for y. So what would be the x-intercept here? This one will cross the x-axis. Yeah?
2.
Yep. 2 would make the fraction 0. Just be careful that 2 doesn't also cause you to divide by 0, because if it does, then that's a problem. And that'd be it. So you'd have all your asymptotes, check a point on each side, and then make your sketch. Okay, so any questions on that? All right. Okay, so homework tonight it's on 234. It's 1 through 7 odd, 9 through 12, 15, 17 to 22, 23 to 26, 29, and 33. I do have some graph paper. I could make some copies of it. Would anybody want some copies of graph paper? Okay, yep, we can do that.